All right, let's talk about black holes. Seriously, they're the universe's ultimate mystery, right? These are cosmic titans that literally warp the fabric of reality and push our understanding of physics right to the absolute edge. So let's take a deep breath and plunge into this abyss to see what's really going on.
This definition pretty much says it all. It's not just that the gravity is strong, it's absolute. The escape velocity, the speed you need to get away, is faster than the speed of light. And since nothing can go faster than light, that means once you're in, you are in for good. It's the ultimate point of no return.
You know, this whole idea has actually been around for a surprisingly long time. It kicked off way back in the 1700s as just a thought experiment about dark stars. Then Einstein's theories made them a mathematical possibility. But for decades, that's all they were, just an idea on paper. It wasn't until we started pointing X-ray telescopes at the sky that we saw their effects. And then, the big one. In 2019, we actually saw the unseeable, the shadow of a black hole. What a journey, huh? From pure imagination to a real-life photograph.
So what is a black hole really? I mean, what are its parts? To get our heads around it, let's go on a little hypothetical tour, starting from the blazing outer edge and heading straight down into its unknowable core.
Okay, so before you ever get to the black hole itself, you run into this, the accretion disk. Now, this isn't technically part of the black hole, it's more like its final meal. As gas, dust, even whole stars get pulled in, they create this massive cosmic traffic jam, spiraling around and around. The friction is so insane that it heats up to millions of degrees, glowing brilliantly in X-rays. It's kind of like the universe's last light show before everything goes completely dark.
Next up, probably the most famous part, the event horizon. Now, what's really important to get is that this is not a solid surface. You can land on it or crash into it. It's just an invisible mathematical line drawn in spacetime. On one side of the line, you could, in theory, escape, but the second you cross it, that's it. Your journey is now one way. There's absolutely no turning back.
And at the very heart of all this is the singularity. This is where our science just hits a wall. Seriously, try to imagine all the mass of a star, or millions of them, crushed down into a point that has zero volume and infinite density. Space-time here is infinitely curved, and our two greatest theories, general relativity and quantum mechanics, just completely break down. They stop making sense. It is the ultimate unknown in the cosmos. But hey, not all black holes are created equal. The simplest version we can imagine is a Schwarzschild black hole. It's perfectly spherical and it doesn't spin. But let's be real, almost everything in the universe spins. So most black holes are probably Kerr black holes. Their rotation is so powerful, it literally twists the fabric of space-time around with it. The best analogy? Imagine a spinning ball in a vat of honey. It just drags the honey around with it. This completely mind-bending effect is called frame dragging.
And these cosmic monsters don't just have different spins, they come in a huge range of sizes. So let's check out the different species in this wild cosmic zoo. So we've basically got three main flavors. First, there are stellar mass black holes, born from the explosive death of a single giant star. Then, on the other end of the scale, you've got the supermassive black holes. These are the absolute behemoths that anchor the centers of entire galaxies, weighing millions or even billions of times more than our sun. And somewhere in between, we've got this mysterious class of intermediate mass black holes. They're kind of the missing link we're still trying to get a handle on.
And don't think this is all just some distant, faraway phenomenon. We have one of these giants right in our own cosmic backyard. Meet Sagittarius A star, the supermassive black hole smack dab in the center of our Milky Way. It weighs in at 4 million times the mass of our sun. Every single star in our galaxy, including ours, is right now orbiting this invisible titan.
All right, now for the question everybody asks. What would it actually be like to fall into one? Let's drop in and explore this ultimate and frankly terrifying thought experiment.
Okay, here's where things get really, really weird, thanks to relativity. Let's say your friend is watching you from a safe distance. To them, you would appear to slow down as you get closer to the event horizon. You'd get redder and dimmer until you just seemed to freeze in time, forever. But for you wouldn't notice a thing. You just sail right across that line, business as usual. And the craziest part? Both of you are right. Both perspectives are correct in their own frame of reference. Wild.
So once you've crossed that line, your fate is sealed.
Because space and time are so warped inside, you could actually watch the entire future of the universe unfold in what feels like just a few moments to you. And then comes the end. The gravity pulling on your feet would be so much stronger than the gravity on your head that you'd get stretched and squeezed. The process has a gruesome but very accurate name: spaghettification.
Now, I know this all sounds like something straight out of science fiction, but black holes are very, very real, and they are fundamental to how our universe is built. But if they're invisible, how are we so sure they're actually out there?
We've got multiple rock-solid lines of evidence. We've literally watched stars at the center of our galaxy whipping around an invisible point at unbelievable speeds. We have directly detected the ripples in spacetime, gravitational waves, that are created when two black holes crash into each other. And of course, we've even taken a picture of one's shadow. They've gone from being a theory to an undeniable fact of our universe.
But maybe the biggest mystery of all came from Stephen Hawking. He figured out that black holes aren't totally black. They actually evaporate incredibly slowly over trillions of years through something we now call Hawking radiation. But this creates a massive paradox. What happens to the information about everything that fell in? See, quantum mechanics says information can never be destroyed, but general relativity says nothing can escape a black hole. So, is it lost forever? Answering that question might just be the key to the next great revolution in physics.